Organic chemistry can be challenging, so let's start this video off by giving ourselves a high five for being here. Okay, it's true that we are proud of everyone for tackling OChem, but this high five was an excuse to introduce one of the keystone concepts for biochemistry, chirality. Chirality means like hands, and, as we hope for all scientific terms, our namesake appendages are a perfect illustration of this concept. Our two hands are the same as each other, except they're not. A pair of hands is flipped so that they match up in a mirrored way but don't perfectly overlap. Our feet are the same, so if you've ever tried fitting your right foot into a left shoe or a right hand into a left-handed rubber glove, you know that it usually doesn't work very well. So what chirality describes are objects that are made of identical parts with identical connections, but that cannot superimpose onto their mirror partners in three-dimensional space. Using a term from organic chemistry, this means that chiral molecules are stereoisomers. That is, they have the same molecular formula and the same connectivity, but their spatial arrangements differ. You can refer back to the Introduction to Isomers module if this idea is unfamiliar. The word chiral comes from the Greek language, so if a molecule can be superimposed onto its mirror image, we call that molecule achiral. That's an important difference between a chiral molecule and an achiral molecule. More on why that's important later, but for now, we want to be able to identify chiral compounds because they figure so prominently in biochemical reactions. You can expect to be tested on this idea, at least indirectly. Let's briefly look at a molecular example, the chiral molecules here for instance. If we rotate the blue molecule on the right 180 degrees, we can superimpose the hydrogen and fluorine atoms of both molecules. Once we do that, we see the chlorine and bromine atoms don't line up. The more elaborate way of saying this is that the two have the same set of unique atoms and chemical connections, but the two cannot be interconverted by simple rotation of a sigma bond. This makes them stereoisomers and chiral compounds. Now, look at these two molecules that are also mirror images of each other. In this case, all of the atoms can be superimposed by rotation, so they are achiral, and the molecules are actually identical. This provides a useful shortcut to identify chiral carbons. Chiral carbons will have bonds to 4 different atoms or groups. This means that if two of the same thing are bonded to a carbon, that carbon is, by definition, not chiral. This can be simple to spot for many of the carbons encountered in biochemistry that are bonded to 2 different hydrogen atoms. Consider glycine. It's the only achiral amino acid in normal biology, and it's achiral because it has a second hydrogen instead of a larger amino acid R group. Now we can start to get a little more detailed. In most examples of chemistry we might care about, there will be molecules with multiple carbons that may or may not be chiral, so the practical applications of chirality get more complicated than a single pair of hands. Imagine our original example extending from the hands to the shoulders. At our hands, elbows, and shoulders, we have the same muscular connections to the same bones, but in a mirrored, non-superimposable way. We might imagine that each of these areas is a carbon with unique substituents. Molecules that are non-superimposable mirror images, like our arms, are called enantiomers. A pair of enantiomers will have the same chemical formula and the same structural connectivity at every single carbon, which means they'll also have the exact same chemical and physical properties. There are 2 exceptions to that last part though. First, enantiomers interact differently with other chiral compounds. Just like trying to shake another person's right hand with your left hand would lead to a pretty awkward situation. Second, 2 enantiomers will interact in opposite ways with plain polarized light, which is light that oscillates in only one direction. Since light is its own unique phenomena, there's not a perfect analogy for that second exception. You can remember that an R enantiomer will rotate plain polarized light in the same amount, but in the opposite direction as an S enantiomer. An important application of this idea in biological systems is the idea of a receptor. As proteins, receptors are chiral molecules overall, and many of them discriminate between enantiomers, usually tending to be highly specific for one over the other due to the specific spatial arrangements of their ligand binding pockets. So, chiral molecules are defined by the presence of chiral centers, which are sometimes denoted by an asterisk or by specific nomenclature-based labels that we'll introduce in a few moments. As we mentioned earlier, you can recognize that a carbon is a chiral center by recognizing that it has 4 different substituents. Bonus points if you also remember that carbon would be sp3 hybridized if it has 4 substituents.